Well, good afternoon, everyone. Welcome back to the webinar series for the ACF. Hope everybody had a good week. We'll give just a couple more minutes to have other people call in, and we'll just get started in a minute or two. So thanks for calling in, and we'll get started just very shortly. All right, we'll go ahead and get started. When others call in, then call in, just catch up to where we are. So again, welcome back to the webinar series. Today we'll be discussing compiling and job submissions on the machine. So far, we've gotten through 4 sessions. Today is the 5th and last session. I've posted several of the sessions that got recorded. The first session we didn't get a recording of, but I'm going to record another session to replace it. But I have put the 2nd, 3rd, and 4th sessions out on our website. So if you're interested in going back and looking at those, feel free to. They're posted up on our website. There's a link that'll take you to YouTube, and that's where the videos are hosted right now. So again, today we'll be talking a little bit about compiling and about job submission. And we'll just go over some of the basics, and we can go into any details that you guys would like to. So we'll start talking about compiling. Compiling is the process of transforming source code into an executable code. It works by taking that source code of yours, it'll translate it into basically assembly language called object code. And then that object code is then linked with other object code to create an executable binary that you actually run. A linker is just a separate program that is used to combine those object files together, adding libraries and functions as need be to make that particular program actually executable. In many cases, the compiler will serve both those functions. So the compiler serves as the compiler, converting source code into object code, and then it will take that object code and then combine it with the other libraries and object codes that it needs to make an executable. So that usually happens in one step. So you don't typically have to use a separate linking program to do the linking. That's usually done for you automatically. There are cases, however, when you may not need to recompile your entire program. You may only need to relink it with new libraries, and you can use linkers to just do that piece of it. Again, a lot of the times the compiler can be used as the linker, and you can use just the one program that does all, both the compiling and the linker as well. On the ACF, we have a couple of different compilers. We have compilers from GNU, and we also have the Intel compilers on the machine. We have compilers for C, C++, and Fortran. If you're looking in the GNU world, it's GCC does the C programs, G++ does C++ programs, and then G Fortran will do Fortran programs. If we look over into the Intel world, you have ICC, ICPC, and then iFort for Fortran. You also have MPI versions of all those as well. So you have MPI ICC and MPI ICCP and MPI iFort. Intel compilers are loaded by default. Since it's mostly an Intel machine, those compilers tend to do the best performance. So we go ahead and load those up by default. You can change those by use of using the programming environments we have set up in the system, which is the preferred way of doing it. Or you can load and unload individual modules, although we don't really recommend that because you can get in a state where you have some compilers from, for instance, Intel, and yet you may still have some libraries from GNU or from other sources, and that could cause you some problems when you go to compile and get your code running. So I'm going to flip over to Terminal. I've already logged into the ACF. We'll look at some of the programming environments we have and how we can switch between those programming environments. So let me switch over to Terminal. And so I've already logged in, so I'm currently in the ACF's login node. And if I do a module avail, it'll show me all the software that's available in the system. And if I scroll through that list, I'll see all kinds of programs that are installed. But what I'm really looking for in this case, I'm looking for the different programming environments that we have available. So if I scroll through here, I'm going to see all kinds of stuff. So we have our programming environments named with PE dash and then the name of whether it be for Intel or whether it be for GNU. So if I scroll through this list, what I'm looking for is that programming environment. And you'll see here underneath all the module files that are in ACF opt, you'll see PE GNU and you'll see PE Intel. So those are the different programming environments we have. And what those do is they set up the environment. They'll load up the appropriate modules for whichever environment you want to compile in. We have many different versions of the Intel compilers. The default version is the 2017.2.17 or 174. That's the default Intel compiler. We have several versions. The newest one is the 174. We also have some newer ones that are new to this year, but we haven't made them default yet. So we haven't really thoroughly tested these yet to see how they perform, but they are available if you like to use them. So like the Intel MPI 2018 version 163. We also have the 128. Right now, default, because it's the tested one that's working the best, is the 217.2.174. We also have a pointer that just points to the latest Intel compilers if you want to just use the latest always. And we'll do all the work in the background to make sure that stays the latest. By default, you can see what you've got loaded up by default by doing a module list command. And it'll show you what modules have already been loaded up in your system when you load in. So by default, we load up the programming environment for Intel. Excuse me. And when we do that, you'll notice that it loads up the Intel compilers, the default version. We also loads in the Intel MPI compilers, the default version. It also loads in a couple other things to allow us to schedule the resources like Moab and the PVS tools as well. And then we have some default applications that get loaded in your environment as well. If you want to switch your programming environment, well, first before we do that, let's take a look at what is in those environments and what is getting set up in those environments. So if I were to look at display what is going on in, for instance, the PE programming environment for Intel, what it does, it sets up an environment, telling me what the PE compiler is, which is Intel. It loads the compilers, it loads the MPI compilers, it sets some environment variables so that my CC environment variable is set to ICC. For C++, it's set to ICC-E. For the CXX, it's set to ICPC. For Fortran, Fortran 77, Fortran 90, they're all set up to iFort. So those set up some environment variables for you to point in your make files for when you're compiling to which compiler it should use as it's running through your make files. If I want to switch programming environments, I can use the module swap command. That's module swap. And I'm wanting to swap, for instance, my P programming environment of Intel to my programming environment for GNU. And when I do that, now if I do the module list, it's going to show what's loaded into my environment. And now I see I have PE GNU, but I also have now the GCC compilers loaded up. It still left the Intel compilers there, but it went ahead and changed everything. And if I were to look at that, I can see what changes happen. So if I do a module display of the PE GNU, I can see it set up a different set of environment variables. So now it's completely redefined what's going to be used in my environment. So it's going to use GCC and G++ and G Fortran. Okay. It did go ahead and load up the Intel MPI because that's what it's going to be using to implement MPI when it compiles the MPI programs. Okay. Okay. So the other thing you could do is you could go in and load and unload those individual modules. So for instance, if you didn't like the particular one you saw, you could, if you wanted to. So if I'm looking at my list of modules loaded up, and let's say I wanted to change modules, so I can do a module avail Intel MPI. That's going to tell me all the modules that I have available for MPI and all the different versions. So I have a couple of versions of the Intel MPI. Again, defaults to 0.174. But let's say I wanted to try one of the other Intel compilers. I could swap this particular version for another version. Again, you could use the module swap. And then I want to tell it that I want to swap my current version, which is this version right here, which is loaded up. And I want to put in maybe this version of the 1.28 to get a newer version, because I want to play around with it and experiment with it and see how that works. And when I do that, that'll switch out those module files, and that'll set my environment now to use the 1.28. And you can do again the module list to see what's currently loaded up. So now I've loaded the .128 version of the Intel MPI compiler. Okay. Here's a simple hello world program. It's hello.c. This is just a simple C program that just spits out hello world to somebody. To compile it using an Intel compiler, if I had that environment loaded up, I would just do an ICC hello.c. By default, it's going to create a file called a.out, but if I want to call it something more useful, I would put in the -o option to that compiler. So I can compile that one. I've got a copy of it here in my directory. So I have a program called hello.c. It's a very simple C program. And it just loads up the default or the typical libraries into the program. It just prints out a message to the world. If I want to compile that, so I'm going to see what modules I have loaded up first, see if I want to use either GNU or Intel. So let's say I want to use the programming environment for Intel. So I'm going to swap back to that module with a module swap. And I want to switch from the PE GNU that I currently have loaded up, and I want to switch back to the Intel module. And when I do that, I can confirm that happened by doing the module list again. So I have the Intel compilers loaded up, and I've got actually both versions of the Intel compilers loaded up right now, and that might cause an issue. I can also unload those particular modules if I wanted to. So if I wanted to get rid of the 128 for fear that they might bump into each other, I can do a module unload. And I could do a module unload of the module I'm kind of worried about might cause problems because I might get some interference there. I can just unload that module, and I can check and see if it's still there or not. And it's now gone, so I don't have to worry about it. So if I'm going to use the C compiler, in the Intel world, it's ICC, and then you have to tell it what source file you're wanting to compile, and I'm wanting to compile the hello.c file. If I do that, it's going to create a file just called a.out, which is pretty typical. So if I do that, I now have a file that's called a.out. And it's set to executable, so it is ready to execute. And I can verify that by making sure it's got the execute flag on it, and it does. So that's now an executable program, a.out. To run it, I can put in a /a.out, and it just runs that program. Now, this program is also asking for a command line parameter, so I can put in my name, and now it does hello Bobby. So it's not a very complicated program, but that's how you compile it. If you don't like that it creates it a.out, you can also rename it as you're compiling it by putting ICC, the name of the source file, putting the -o, say I want to output this as something else, and then you could call it, for instance, I'll call my program hello. When I do that, now it's created a hello program. I can then run that by just doing /hello and then my name. Now I've got an incredible program that says hello world and my name on it. So if I wanted to compile that with GNU, I would do a very similar thing. I would switch my modules. So I do a module swap PE Intel for PE GNU. And it gave me some error message about the Intel MPI, so I'm not going to worry about that message right now. I'm just going to compile. This is a serial program, so I don't have to worry about the MPI at this moment. So when I'm using GNU, it's GCC to do C programs in the same kind of format. I'll tell it to use the source code. If I want to name it something else, I can do the -o, tell it to call it something else. It compiles, and I do the /hello again, and then my name. Program works the same. It's usually recommended that if you're compiling your program, you should use as many compilers as you have access to on a system. Depending on the compiler, they compile differently. They might do order of operations different inside the compiler. So you might get better performing code out of one compiler versus another compiler. So it's important to try any compiler you have access to, just if you're worried about performance, getting the most out of the machine. In a little serial program like this, I'm not going to see any performance differences between the compilers, so it doesn't really matter that much. But if you have a larger, more complicated program and performance is more of an issue, you want to try it with the different compilers. All the compilers have different options for optimizing the compilations, and so you want to make sure that you look through the manuals and make sure you know what all the different options are. And you'll pick the couple of options that make the most sense, and you'll test them out and see what code runs the best with which compilers and which options. Another thing you want to do when you're using different compilers is make sure you check your results of your calculations, because if they do calculate differently, they might come up with different answers, in some cases not as precise an answer. So you're really looking for the compiler that gives you the best performance and also the more accurate and precise results. So it takes a little bit of trial and error sometimes, a little bit of experimentation. And usually if you're dealing with a larger, more popular code, somebody out there has probably already done that optimization. They'll know exactly which options to give to which compiler to both give you the best performance and to give you the best results. Same thing, if you're doing an MPI program, it's much the same. So this is just a simple MPI program, except you're going to use a different compiler. You're going to use the MPI CC. So we can take a look at that as well. So I've got a simple little MPI hello program. So if I look at my MPI program, whoops, .c. So this is just a simple hello program that runs in parallel. It simply just says hello world from each processor it happens to be running on. So if I want to compile that, I'm gonna switch back to the Intel. Let me see where I'm at. Module swap. Let me do a module list. I forget where I'm at now. Module list. I have PE GNU loaded up. So I want to switch back to the Intel. So I'll do a module swap. PE-GNU. And I'll switch that to my programming environment for Intel. All right, when I do that, now it's loaded up MPI ICC. And then I want to compile my source code, which was MPI hello.c. And then I want to give it another name, so I'm going to give it, I'll just give it MPI hello. So that'll create an executable called MPI hello. Now, if I try and run MPI hello right now, I'll get an error. So right now it's only running on one processor. So it's really just saying hello from process 0 of 1. So it's running just on one processor. If I wanted to run that in parallel across multiple nodes, or if I wanted to run that across different different cores on the same processor, I'd have to use the MPI run command. But if I just try and run the MPI run command from here, I should get an error message because I'm not in MPI environment right now. Oh no, it's working just fine then. So yeah, that's working better than I thought it would. So now it's running this across all the cores on this particular node. I'm running on a login node right now. And now it's saying hello world from each of those processes. So from process 0, from core 0 all the way through to core 15. So that's out of all 16 of those. And it comes in random order. There is no set order in which process runs at what time. So that's how you compile both a serial code and then also a parallel code as well. Are there any questions on just simple compilations like that? Here's where we can swap programming environments. And again, we've already looked at swapping individual components or individual compilers or individual environments on your system. It is best to switch the entire environment by doing the PE Intel, the PE GNU. Switching them individually like this can get you in trouble because maybe there's a library that would have been loaded up if you loaded up the Intel programming environment that would have been missed just by loading up the compiler itself. There's a little bit of experimentation there that you can do to see what is the best mix of things for you. All right, so we've already kind of discussed this. So it's always best to try every compiler you've got available to you. On the ACF, we currently have the 2 compilers. On some other systems, you may have compilers from the manufacturer, like if you're running on an IBM system, you might have an IBM compiler, as well as a GNU compiler, as well as an Intel compiler. You might even have a PGI compiler, you might have a Pascal compiler. There's several companies out there that create these compilers. It's just a matter of what are available to you on any given resource. So make sure you use all the compilers available, look at their options to make sure that you find the right ones. Each compiler favors a certain kind of optimization, so some work better with certain options than others. And again, that's either a trial and error or somebody in your community that's used that piece of software and knows what is the best options can give you that information. And a lot of times Google is your friend and you can search out what are the best options for a particular application with a particular compiler. And then the last bullet's very important. You got to test your answers very carefully. Sometimes the order of operations may be different between the compilers and even between compiler versions. So you may have been running with a particular version of compiler for a year or several years, and they switch to a new version, and you may get different answers. So you need to make sure that you verify the results, particularly when you're switching between compilers, even if it's the same compiler in just a different version. And then you may have to come up to and decide whether the highest performance speed-wise or whether precision is more important to you. So it just kind of depends on your particular application and your particular problem as to what's more important. Is it better to be faster or is it better to be more precise? And that'll be a decision that everybody has to make in their own individual cases. So there's all kinds of compiler flags with GNU, the -02 and the -03. Those are some popular compiler flags that turn on more information for debugging. It'll make your code slower, but it also provides more information that you can go back later and use a debugging tool to see what's going on. So those are pretty popular. If you want to learn more about the different options, and there are dozens, if not hundreds of options, you can do man G4tran or man GCC or man G++. It'll give you all the information about all the different flags that are available. In the Intel compiler world, the -fast is a popular option. It really shoots to make your code perform fast, hence the name fast. The Intel man pages aren't available in the ACF, but you can still get help on those Intel compilers by doing the compiler name and then -help option. So it'd be ifort-help to get information about the Fortran compiler from Intel. You can do ICC-help to get information about the C compiler. And you do ICPC-help to get information about the C++ compiler. And it'll list out all the options that are available. We can take a look at that. And one thing you need to be careful of is that it will spit out a lot of information, and it'll blow past your screen. It'll fill up your screen buffer, and you won't even be able to scroll back to see it all. You can add the pipe symbol and then just pipe that to more, and then that will give you the ability to scroll through a page at a time. So you can scroll through a page at a time and look at all the different options that are available. Again, like the -01, -02, -03, these will optimize for different things. Optimize for maximum speed and enable more aggressive optimizations that may not improve performance on some programs. And you can read through all these options and find the ones that work best for you. A lot of the times when you download a piece of software, it's already going to have those optimized compiler flags, at least in the documentation for that piece of software, or it might even be in the make file for that particular piece of software. When it compiles, it might already have all the correct flags that optimize that program the best. So make sure you read the documentation carefully on any piece of software you're trying to install. In the typical way of getting a new program and installing it, you're more than welcome to install any program that you're interested in, either in your scratch space. If it's small enough, you could put it in your home directory. This here is just an example of how that typically goes. This is pulled out of a previous presentation we did on compiling and making and installing software. Normally you'll get the software using a program called wget, and it'll be in some website somewhere. And you can usually find the link on the website of that particular piece of software. Usually they're going to be in the form of a tarball, which is a particular kind of archive file that is both archived and usually zipped up to save space. You're going to download that, and that's what this does here. That just downloads that particular file to somewhere, whether that be in your home directory or in your scratch directory, or maybe a project directory if you have a project directory. You would open up that tarball by untarring it, and that's what this command will do. You would then go into that directory. You'd run a program called configure, so you do a .configure. And one of the options for the configure program is do the -- prefix and tell it what directory you would like to install that program into. This could be your home directory, this could be your scratch directory, this could be your project directory. You would just put that in there. What configure does is it goes through, it checks your system to see what compilers you have loaded up, what your environment looks like, and it creates a make file. The make file is used then by the make program. So the make program will go through and compile all those files that came with that particular program. And then you'll do a make install, and that just installs the program correctly. You would set your path up correctly, and then you could run that program. This is good if you find a program that you're kind of interested in, you want to learn about it, you want to play around with it and see if it might be useful for you. You're more than welcome to try and install any software on the ACF as long as it's licensed for open research. You're welcome to install that on the ACF, whether in your home directory, your scratch directory, your project directory. If you believe it's a piece of software that's going to be used by several people could be 2 people, it could be 30 people, you can send in a software request and ask for us to install it globally, and we'll evaluate that request and we can install it. If you decide you just want to install it for yourself to experiment with it and understand it better, we can certainly help you install this in one of your directories. So you're more than welcome to reach out to us, and we're happy to help you install some program. We've got a lot of experience installing different kinds of software, so usually we can figure it out. There are some harder pieces that it might be more of a collaboration between you and us to try and figure out how to install a piece of software, but that's fine. And that's actually better because we like to do things more collaboratively like that. Does anybody have any questions on kind of the basics of compiling and what compilers we have available, how to switch out programming environments, or any other questions like that? If not, we'll move on. We'll start talking about the batch scheduling system that we have in ACF and about job submissions and things like that. So on large resources like the ACF and others, the issue comes down to how do you make the best use out of those systems. You have users that are competing for these computational resources. So, there could be dozens or hundreds of users on a given system, all of them competing for some time on that machine. So how do we launch those jobs? How do we schedule them fairly? How can they run without the user having to sit there and watch their screens the entire time waiting for their jobs to run? And then you got to make sure that you don't allow one user to hog all the resources up. So the best way to do that is through a batch queuing system, a batch scheduling system. And the basics behind the batch scheduling system is it accepts inputs, your input jobs into a queue, and then it launches them as those resources become available. Many machines use the PBS system or the portable batch system. We use a version of that called Torque. It's still PBS, but it's an open source version of PBS. PBS is now licensed software, so you have to pay them large sums of money every year to actually use it. And so we use a free open source version of that called Torque. PBS was originally developed for NASA back in the 1990s, so it's been around for several decades now. So it's almost ubiquitous in any kind of large resource. There is a difference between schedulers and resource managers. So a scheduler decides when a job can be run based on its scheduling policies. Those policies could be anything. Could be the user priority, could be the length of the job, could be the number of nodes requested, could be the length of time in the queue. So there's all kinds of different knobs that can be adjusted to determine these different scheduling policies. The resource manager, like Torque, its job is to go out there and reserve and put a reservation on the particular resources. So imagine a user has asked for 2 nodes. The Torque, the resource manager's job is to go out there and put a hold on a couple of those nodes for that user to be able to run jobs on them. Then behind that comes the scheduler, which now sees that there are some resources that have been reserved for scheduling, and now it goes through its jobs that it has in its queue to figure out what order those jobs should go on to that particular resource. The ACF for our resource manager uses Torque, which again is the open source version of PBS. And then for scheduling, we use a program called Moab, and that does the scheduling piece of the scheduler resource manager combo. All right. So there are limits for wall time, so you don't have infinite wall time. There's limits for number of processors, so you can't ask for the entire machine all the time. So if a request exceeds some limit, whatever that limit happens to be, the job will usually automatically get rejected. Now, sometimes the job will go ahead and get put in the queue, but then it'll never run because it may be asking for something that just doesn't exist. And when those cases happen, then it's just kind of on us at the ACF to see that a job is stuck because it's asking for something that doesn't exist, or it's asking for something that's beyond some limit and it's somehow snuck through and the scheduler didn't catch it. So you may at some point get an email from us saying, hey, this particular job won't run. Here are the reasons why it won't run. And then we'll work with you to fix your job script so that we'll actually get that job up and running. So usually, and this is kind of a very generalized rule, the schedulers usually prefer smaller jobs and they usually run first, because usually it's easier to fit a smaller job in an opening than it is a larger job. So what the scheduler tries to do, it'll look through its queue of jobs and it sorts them based on all the priorities, and it'll give them a priority number. And then it goes back through and it tries to schedule those jobs. It usually tries to schedule the biggest job it has space for first, and then it goes and tries to find smaller jobs. So usually what will happen if somebody's requested maybe 10, 15 nodes or something like that, and they want it for 6 days or something of that order, it'll try and schedule that job and put a reservation on hold for that job. If there are smaller jobs that can maybe run in that space before the big job could start, the scheduler will try and get those smaller jobs put in there so that they can run quickly, get out of the way, and not stop that bigger job from running. So the smaller jobs typically have a better way of doing what they call backfill. So if there's any gaps in the scheduler where it's looking for maybe a small job that could fit into a small time frame or into a small node count, the schedule will do its best job to try and get those smaller jobs scheduled around the larger jobs as best it can. And when we're talking about size of a job, we're really talking about the number of processors and then the estimated time of how long that job is going to run. So those are the two factors that really tell you how big a job is. And that information comes from the user submitting the job. So users will submit the job about the number of processors that they want and then an estimate of how long that job will run. And the scheduler uses that information to try and figure out how to schedule that the most effectively. A friend of mine once said this, so I'll put it in the slide, that it's like the inverse of the Price is Right. The idea is to give your lowest estimate possible without going under the true time needed. That's always the best strategy, but that can be very difficult. It's sometimes difficult to know exactly how long your program is supposed to run. And even if you've run it several hundred times and have a good idea of how long your job would run, things on the system might have slowed it down. It may have actually run longer. And sometimes you want to pad it, but you don't want to pad it too much. Use the fewest processors that you can get by with. That's always a good idea. If you don't want to overestimate, if you can help it, it just makes it harder for those jobs to get through. So you want to try and give as best an estimate as you can. Use the fewest processors in the shortest amount of time, and then you've got a much better chance of getting through the queue quickly. If you just get in the habit of just always asking for the same amount and the same amount of time, whether that's accurate or not, you can find sometimes those jobs will just kind of get stuck and they'll just be there for a long time. Now, as you probably already experienced, if you reach the end of your estimated time, Torque will terminate the job for you. So if you've asked for 20 minutes, but your job runs for 25 minutes, it will terminate your job at the 20-minute mark. And the way you do that is you're going to write some scripts to tell Torque what you want to do when the job is launched and all that kind of stuff. So here's the basic script format for a job script. You always start out the first line with whatever command line interpreter you want this particular script to be interpreted with. On the ACF, we usually use Bash. We also have C shell. We also have Z shell. Whichever one you're wanting to use is where that would go in the very first line of your shell script. There are three different options you've got to have. You've got to have the PBS-A, which is the account. So that would be your project ID. You've also got to tell it how many nodes do you want and how many processors per node you want. If you don't put the processors per node, it just defaults to using all of them. But maybe you only want to use half the processors per node because you'd like more memory available for your program. You also got to tell it what kind of wall time you expect to use. Again, try and get it as realistic as you possibly can. The next thing you'll do is you're going to change into your working directory, and that's the working directory should usually be on your scratch space. That's usually safest. And that PBS_O_workdir, that gets created for you automatically. So that environment variable gets created automatically as your job starts to run. And then the last line there is going to be the execution line. This is telling I'm running an MPI program, so I use the MPI run command, and I want to run across, in this case, I want to run 48 copies of that. Now what that's going to do is going to try and run 48 copies of that program on just that one node. So you might want to reduce that number down to 16, and that way you're only running one copy of A.dot out, and you get the better performance that way. But you could also put in the -N48, and it would sit there and you let 16 run, and as soon as those 16 ran, you try and run the next 16 and the next 16. That's usually not the best way to do it, but that is an option that you could do. It won't give you the best performance, and you'd probably run out of time, so you got to be careful about that. There are tons of different PBS options you can use, and instead of writing them all down, what you can do is you can go over to our website, and there you'll see all the different PBS options that are available to you. So the ones that you really have to have are going to have your account, and that's going to be your project ID, whatever that happens to be. You need to tell how many nodes you want to use. You got to tell how much wall time you need. Other PBS options, there's the -O. You can write your standard output to some other file. By default, it's going to write out all your output to a file, and this allows you to name that file. Instead of just the job name .output, it can give you an option to write out a different file with all your output that's coming out of your program. All right. You can also tell it to write the standard error to a particular file name. If you don't include the -O or the -E, it by default will create an error file and an output file in your PBS working directory. If you put the PBS-J with either the OE or the EO, it'll combine both of those and just put it into one file. So if you don't really like seeing two separate files for your output and for your error information, you can combine them with the -J. You can also use the PBS-M, all right, and that will give you an email. So this will send an email to the submitter when the job aborts. So if your job quits unexpectedly, you'll get an email. If you want to send an email when the job begins, you can use the -MB, and you can also use the send email as when the job ends, and that would be the -E. You can actually combine those if you want to, so you could do the PBS-M and then ABE, and then for every job you would get 3 emails, one when the job starts, one when it ends, and optionally if it aborts in the middle, you'd get a 3rd email for that. The big M, the capital M, so PBS capital M, it'll tell what email address to send those emails to. So you'd really want to use a capital M and your email address, and then the small m, ABE, to get all the information emailed if you wanted to. All right, if you do the -N, that's going to set the job name to whatever you name it to. You can also put a -shell. Most people don't do that. You can also use a -Q. Now in the ACF, we really only have 2 queues. By default, everybody goes into the batch queue. We also have a debug queue. The debug queue is a queue designed for short debug jobs. It's 4 nodes, and the job can't run any longer than 1 hour. So you're welcome to use the debug queue for short, quick turnaround jobs where you're just trying to see if something works. And that's -Q and then the word debug, D-E-B-U-G. There's also the feature option, which will select different features. In our case, the feature usually refers to which of the nodes you'd like to run on. And I'm going to bring that down to a little bit further. There's another option that's important, is the partition option, -L partition. In the ACF, we have several different partitions that you can run in. So you can see here that if you run on beacon nodes, and beacon nodes are the 16 core nodes, the partition name is beacon. So you'd say partition equals beacon if you want to run on the beacon partition. If you want to run on the row partition, partition equals row. If you want to run on Sigma, Sigma Big Core, or Skylake, you're going to run in the general partition. So you'd say partition equals general, and that would put you either in Sigma, Sigma Big Core, or Skylake. If you want to run in a particular one of those 3, you would have to say something along the lines of, I want to run in the general partition, but I want the feature of Skylake. And that would make you run in the general partition, but then it would ask for Skylake nodes inside of that partition. Okay. You can also run interactive jobs. So interactive jobs, they still get submitted to the batch scheduler. They still get scheduled onto the ACF just like any other job. But what you'll get back is you're going to get an interactive shell that allow you to run programs interactively. So you're not waiting for the job to run in the batch schedule, then send you some emails. You're actually logged in. You've got a terminal. You can type in commands and run commands from the terminal and get quicker feedback. To do that, you'd run the qsub command, qsub -I, minus capital I, -A, your project ID, whatever that happens to be. You do a -L, that's a little l, nodes equals whatever. There's up to 4 in the debug queue, so if you're using debug queue, you can't ask for more than 4. And then the wall time is default for an hour. You can try and ask for more, but if you do, you'll be waiting for a long time. I wouldn't ask for any more than 1 hour. If you wanted to run in the debug queue as an interactive job, you would add a -Q, -Q space debug at the end of this line to be running in the debug queue. Once it'll wait for a few seconds, might take longer depending on how many people are using the system at a given time. Eventually you'll get a shell pop back up, and then you can run commands. So you could then change to your Scratch directory and then run any MPI run command you wanted to, just like you were doing in your job scripts. So we've looked at the PBS torque options. What questions can I answer for you guys? So I have posted the last 3 sessions we've had. I posted on the website. It's on the NICS website, nix.utk.edu. You can look under Education, Outreach, and Training on the links and get to Event Archive, or you can just go straight there with this link. If you have any questions, help@nix.utk.edu, or you can email me directly at rmwjr@utk.edu. If you guys have any questions, please let me know. If you've sent me an email in the last week, I haven't gotten to them yet because I've been out of the country for the past several days, and I'm behind on my email. So I am getting through my email. If you sent me an email, sorry I've not responded to it yet, but I'm getting there. If you have any questions, email me, email help@nix.utk.edu. If there are any other topics, this is our last scheduled session for these webinars. If there are other topics you'd like to discuss, we can schedule future webinars. Send those to me and we can try and get those scheduled. If you have no other questions, I am done if you guys are done with me.
Robert, what would be the maximum wall time?
So the maximum wall time right now, we have it is if you're in a priority project, which is somebody who's invested, and I think depends on what project you're on. So we have a campus-wide access project, and then we have individual projects. If individual projects have been investors, they've invested some money, then those have a 6-day wall time. For the opportunistic folks, the backfill folks, they have a 24-hour wall time.
Okay, and how do we, request for increasing the wall time during when the job is still running?
If the job is still running and you need to request an extension, send an email to help@nix.utk.edu and just include the job ID and say, I need it extended till this amount of time, and we'll look at your project, and if you're in an investor project, we'll extend it up to however long it needs to extend it.
Okay, thank you.
You're welcome. Any other questions? If not, thanks everybody for attending. Send me any emails. If you have ideas for future topics, please pass those to me. If not, everybody have a fantastic weekend.